6 or 8 different sets of muscles around the abdominals which provide that support. And so we tried to model all of them, and we found that, yeah, the amount of force. And the other thing is, with scoliosis, most of the forces are when you're bending over and bending back. Not so much when you twist, unless you have scoliosis. Because if your spine is already twisted and you want to bend over, then there are huge amounts of torsional forces on your spine, which are not normal, not found in normal skeletal behavior. So people who have spine curvature are likely to damage their spine much more in the future as they grow older anyway. So these are lessons, people. Okay. Also in NUS, but then also when I moved to Australia, I worked with this gentleman on the top right. So we're talking about tissue engineering a little bit already. And, oops, that's Dietmar, not Dietmat. I have to spell his name right. Dietmar Hutmacher. Also, if you look him up on Google Scholar, you'll find he's got about 50,000 citations as well. And his specialty is in tissue engineering. More recently, he's moved towards things like soft tissue engineering, and in particular, things like female breasts, people that have had mastectomies, breast removal, and looking at also cancer of the breast as well. This is partly because his wife developed breast cancer, and he wanted to sort of try and started to study the area. She got a treatment, and she was fine. But while he was sort of helping her and going through that process with her, he then started to focus a little bit on that. But also partly because he didn't see what was happening, or didn't see a lot of development in bone tissue regeneration. This is what I was mentioning earlier. This is the gentleman I was talking to you about that was essentially now is concentrating more on creating three-dimensional models for in vitro testing to help with things like drug protocols, diagnostic methods, looking at studying cancer growth through models, experimental models rather, and then trying to create predictive models based on that kind of information. He's still doing stuff on scaffolds for load-bearing bones. And at the time I was working with him, I helped him develop the machine that printed the scaffolds. Basically because we were working with a blended, the polymer was polycaprolactone, PCl, and we were filling it with a ceramic powder, tricalcium phosphate, TCP. So we were building PCl TCP scaffolds. And the trouble is that when you blend these materials together, it's extremely viscous in the melt. And 3D printers, conventional 3D printers, would not extrude. They would extrude, but only in ratios of up to about 15% by weight of the TCP. And we wanted higher. We wanted at least 30%. So what I did is we developed, my team, we developed a screw extruder mechanism, which then allows you to apply much more pressure at the tip and therefore extrude higher density and more viscous materials. Sorry? Yeah, we looked at the nozzle. So we actually built the screw feed as well. So it was kind of like a screw extruder, but vertical. But the trouble is if you want a screw extruder, screw extruders are usually this long. Okay. It's not a good idea to have a 3D printer with a print head that's this big. So we tried to sort of look at, so another thing that happens is you usually, you gradually heat the material up rather than just have one area cold and the other area hot. So in a normal FDM machine, the heating area is this big. So that has a significant effect on the flow characteristics of the molten material. So we had a chamber which was this big with heating segments in different regions. We had a nozzle which was a more gradual lead-in and other factors. So there's a lot of head nodding there. You understand what I'm meaning there. There's a lot of, when you start looking in detail and you want a particular problem solving, then you have to look back to basics. And that's what we did. Sorry, say again? We didn't preheat the material. We pre-blended it. So we didn't just load in powder and material simultaneously. We used a twin screw mixer to create powder particles which were already blended. And the other thing is that sometimes we also experimented. So if you've got a ceramic and a polymer and you mix them together, they don't bond together. And some of that you can use other additional additives like what they call surfactants, which activate the surface of the ceramic, sort of etch the surface, which allow for better blending. Another might be a cross-linking mechanism to try and help cross-link between the ceramic and the polymer. So these are things that we've experimented with to try and find out what we've done. All bearing in mind that if you use these materials, they also have to be biocompatible. Okay? So this becomes problematic. Okay. But we had some bit of success. Come on. Why isn't that? Oh, okay, right. Oh, I see. Yeah, sorry. That's just a thing that's showing. That's the scaffold. So just to explain a little bit what's going on is that, yeah, a scaffold is supposed to be a home for cells. And eventually those cells are supposed to grow, and there's a variety of techniques, but if you're using PCL, your intention is for that PCL to eventually degrade. And at the same time, these cells to integrate together and to create new bone. And as also mentioned in the break, that's a problem, because what happens is, as the degradation takes place, the first thing that happens in the polymer is the molecular weight reduces. So it doesn't physically, it doesn't geometrically degrade. So it doesn't dissolve away, it just becomes more fragile. And then eventually it will degrade. The trouble is that what's happening, therefore, is the scaffold is reducing in weight, but the cells are not catching up in strengthening the bone. Eventually, the cells will regrow, and the scaffold will disappear. But you have a classic curve, which was originally discovered by guys at Drexel University in the US, Wei Sun, where he showed that this happens. And the trouble is that the low point, that scaffold could be, or the cumulative effect of the scaffold and cells is weak, and it may break apart. So Yeah, you could isolate it during that period and let the cells regrow, but that might take a long time, and it's still potentially problematic. So the idea is this is the isolation. So these are plates which are put in place, which eventually will be taken away, and hopefully the defect is repaired. That's the principle. Reality is somewhat different. This is just a bit of understanding of what we got. So you have biocompatible, you have bioresorbable, i.e. The biological material can reabsorb the material that it's replacing. Osteoconductive and osteoinductive materials which result in a bioactive. So you've got biocompatible, biodegradable, bioactive materials. And as I said, also bioinert, if you like, which is probably the biocompatible way to describe it. Okay? Ideally, you also want mechanical stability during the whole process. And that's where the problem occurs. Being able to achieve all of these is not possible unless you use more than one material. So this is kind of like the theory behind the whole process. Sorry, say again? I can't hear. They're talking in front of you. Multi-phase? What do I mean? Different materials, basically. Materials which are, they can either be the same material but in a different state. This could be crystalline state, or it could be solid and liquid, perhaps, but that's not usual. But we are more likely talking about, in our case, we were talking about polymer and ceramic. So those are two materials which have a different sort of phase relationship. Okay, they have different purposes mechanically, okay, and biologically. Okay, so having more than one material allows you to share the properties of one material with those of another, and therefore giving you a wider variety of capabilities. For example, the polycaprolactone is a biodegradable material. Okay? The tricalcium phosphate is a bioactive material. So those are two properties which are great, but cannot be found in both materials. So you have the biodegradability, which allows you to get rid of something while the cells take over. You have the bioactivity, which helps the cells to regenerate and gives them something to hold on to and work with. So by having both of those materials together, then that gives you a multifunctional part. You've got two materials, two different types, two different phases. So you might really say these are kind of the phases, if you like. Yes? I was hoping somebody wouldn't ask me that. Inductive is it induces bone growth. So it encourages bone to grow. Conductive is it accepts bone growth. Yeah? So it supports bone growth. So inductive is probably better in a sense then, because you're not only maybe supporting it, but also encouraging it. The thing here is that quite often, again, you would use more than one material. So you might find that there's a material which is sort of like a glass-like material, which is good strength-wise and produces a good scaffold. But then you might have a coating which encourages the cells to regenerate, which is the inductive, osteoinductive. Okay, so So I guess, yeah, so that's basically it. So there's a lot of work that's carried out on coatings. Sometimes you make a scaffold out of a material which is quite easy to process, but is not very bioactive. What you then do is you might, however, then do a coating, and I've seen coatings of hydroxyapatite, for example, which is quite a bioactive material. Okay? But then you might also have some more advanced coatings. Some of the work that I was involved with here was creating homes for coatings which are very highly bioactive, which are protein-based coatings. So in this case, we were looking at, say, what we call BMPs, bone morphogenic proteins. So these do not very well attach themselves to the surface of a scaffold, which means that if you have a scaffold and you put proteins into the scaffold and you put them in the body, probably within an hour all those proteins have distributed around the body and they're not actually being very helpful in the regeneration. So you want to be able to keep those proteins in place. So the method that we were using is we used a material called heparin sulfate, which is a sugar. It's a type of sugar. And that one you can coat onto the surface of the scaffolds quite well. And if you, what we call functionalize it correctly, that then also allows to attach the proteins. And they do what they call hydroxyl bonding. So you have on the molecule, you have an extra hydrogen bond, and that allows, I think, for the hydrogen. Now I'm looking at materials scientists, so they're probably talking rubbish. But as I understand it, basically what happens is the hydrogen atoms, those extra hydrogen atoms, bond together, and therefore the proteins don't wash away quite so easily. And the problem with heparin sulfate is that if you align the sugars one way, you get lots of hydrogen bonds. But if you align them the other way, they actually bond together, and you just get one at the end, which is not very helpful. So the idea is to try and get these sugars to lay flat rather than stand up on end. That again is, as I understand it, that's in a very simplistic way. Okay? My microphone's rumbling. Now we move on a few years and I go to Deakin. And some of you might also recognize this chap that I've been, oh, yeah, actually not this chap, that chap, okay? So that is Mazur Mohammed, who was my postdoc, and he used to like mountain biking. So he used to like going out into the mountains in Australia and running down hills on his bike. And one day he fell off and put his brake lever through his nose, which was quite nasty. Not really nasty, but enough nasty for him to go to a surgeon who then had to scan his nose, and he then had, he was looking at this and said, hey, can I keep that data? So he got his own data of his nose, and he was making models of his nose quite happily on our 3D printers. So yeah, so that was Icky, or Mazur. He was a specialist in microfluidics. And this is an area I haven't really discussed yet. sort of has some relationship with medical. Many of the microfluidic type devices are being designed to help diagnose and detect particular medical conditions. And the idea is to create what is commonly named a lab on a chip. And we wrote a paper actually on this where we said it would be great if these labs on the chips would move out of the lab and into the real world, because a lot of these lab on chip devices, they don't work very well outside of the lab. And what we were working with was another guy called Steve Haswell who's quite famous in that space, trying to develop new lab on chip technologies. Somebody said something? Yeah, so there's a lot of things that you need to control in this process. So because, really what we're doing here, for example, you put liquid down here, and because of the flow characteristics, then the liquid that goes through here takes longer to get to this point than this point. So this is what they call a delay channel. But there's all sorts of different things that you can do. You can see how liquid can be chosen to move in particular directions and not in other directions by changing the dimensions of the tubes. You can inject these in droplet form, so they go in sort of like pulsatile movement, and then mix them, and you can put reagents in at various times. And so the idea of we were looking at was a device that you could print, that you could injection mold, and then equip with all of the reactors and stuff, materials, and then use your mobile phone and the camera on it to detect the actual movement and do things like microfluorescence and other interesting things. We weren't really using 3D printing for this, but we were then looking, well, some of this might even be better if you could print these channels in 3 dimensions. So for example, there's examples of helix-style printer mixers, micro mixers, where you can mix materials in very precise ways by moving the fluids through 3 dimensions. It's very difficult because creating reliable channels in 3 dimensions, which are in the order of a few microns in diameter, is not easy. And then you've also got to think about the actual surface texture so that you don't get shear flows in those channels as well. So it's an interesting problem. I think there's a lot of potential in there. It's another area. People in biochem, that area in particular, there's a lot of interest and potential in there. So this is Icky and his nose. And we had a printer called a Connex, which is from Stratasys. It's based on technology which was developed in Israel from Object. And that printer has a particular interesting characteristic in that you can vary the mechanical properties of the material inside a part. So polymers, yeah. So you can make rigid and flexible polymeric materials. So basically, this nose is flexible. And what you can also do is you could model the cartilage inside the nose, so that would be more rigid. And so you can do a lot of very interesting and precise anatomically correct models. It's a photopolymer. It's basically, so it's an acrylate of some kind. So yeah, it's UV cured, but what happens is that the curing process results in a different shore hardness depending on the mixture. So what it has is, actually has, for the Connex machine, it has 3 print heads. So one, they can be either a mixture of colors, so you could make a color part, or a mixture of materials, so you could make the soft and hard parts. More recently, Stratasys has introduced another machine called the J750. So the J750 has 4 print heads, so it can do both color and shore hardness in the same machine. This one, you can either do color or hardness. You can't do both. And, oh, now I need sound. Are we okay? Can we use sound? What I can do is I can hold the microphone. Okay. Right, so let me make sure that, okay. Let's see if it runs first.
A Geelong woman has become the first...
Hang on. Just drop out a minute. Oh, we do have the display audio. Okay. So how do we? Okay, I'll take it off. We'll do that later. Oh no, it's also the display. Okay. Oops. Yeah. I'll do this. Right. We're good.
A Geelong woman has become the first person in Australia to
okay?
receive a new ear through the wonders of 3D printing. It's a replica of the one Colleen Murray lost in an accident as a teenager more than half a century ago.
Trying to find the microphone.
It's been a long 55-year wait for Colleen Murray to have her left ear replaced.
Wow!
Seeing it for the first time was overwhelming.
I hope that it's because it's good, not bad.
That's wonderful!
After losing her ear in a car crash, she says the prosthetic now makes her feel complete.
I was born with 2 ears, and I wanted 2 ears, and you've done it for me. Thank you very much.
That's all right, it's a pleasure.
Colleen's lifelike new ear is the first in Australia to be made using 3D printing technology.
What we offer with our techniques is a like-for-like 100% reproduction of that patient's own anatomy, which you just can't ask for better than that.
The process began with 3D medical imaging of Colleen's head. Then, by isolating her right ear, technicians at Geelong's Deakin University were able to use data to print a digital mirror image, which became the model for her new prosthetic. Using the 3D printed model prosthesis at the Royal Melbourne Hospital, were then able to create Colleen the perfect ear. A mould was produced for the silicone ear before the final touches were made, preparing Colleen's new body part. Months were spent perfecting the new ear, which snaps magnetically onto titanium stumps surgically implanted into Colleen's head. A piercing for earrings was also on Colleen's wish list.
I've had to hide half my face all my life because of it, and now I'm not going to.
Brenton Cadd has been making prosthetics for 40 years.
The shape is much better, the size is the same, and that's all due to the 3D printing.
Other body parts are also being printed in what could become a major industry for Australia.
We believe as well there's only maybe 1 or 2 examples in the world as well, so Australia could physically be leading the world in this capability.
Colleen says her new ear will give her a new lease on life, and she's now ready to show it off.
I'm going to find a good hairdresser and get a really good haircut to suit around the ear.
Karen O'Sullivan, 7 News.
Remarkable story.
Okay. So this was some work that we did in. So this is just a good example of being able to actually do something which is for shows that it enhances somebody's life, and I think that probably everybody in this room is here at least partly for that purpose. The fact that not only is this a useful, an interesting scientifically engineering technical problem, but also that it helps with life improvements. So great example there. So I should hang on a minute. I noticed that I've not. Let me just do some editing on the fly here. There we go. So this led us to some interesting work in relation to this this technology. There was a professor of anatomy, or is a professor of anatomy at Monash University in Melbourne, called Paul McMenamin, who has been working in this space for quite a long time in creating anatomically correct models for teaching purposes. This is one of his models. This is done using the color powder printing method, what was originally called the Z-Corp process, part of 3D systems types of machine. It's basically a powder binder technology. Now the problem with that technology is that a part that big would be very heavy and also very fragile, and they break very easily. We started looking at the possibility of doing this with the Connex machine to create models. So this is still Mazur's nose. But now you see he's now done a lot of segmentation of the model from the CT data set to segment out the different cartilage zones in there. And there's quite a number in there. I can't remember how many he told me. It was about, I think something like 18 different segmented models inside each other. They're all encapsulated inside each other. And what he's done is color-coded them so that you can see one relative to the other. So this allows you, an anatomy student, to understand the structure of the nasal cavities, the cartilaginous methods, the soft tissue processes around there as well, and can be a very sort of beneficial process. I haven't got it with me at the moment, but I will try and dig it out. There is actually another video which I can show you. I'll probably show you later in the week of this being used in an anatomy class of this technique, this approach, using low-cost 3D printing. One good example of why this is beneficial, Paul was asked to go to, can't remember, I think it was a country in Africa, and at the time they were under an Ebola alert. So that country was not allowed to have cadavers in its medical schools. And so it was becoming quite difficult to teach medical students anatomy and related topics when you don't have any anatomy to actually look at, other than what was in books or what you can get from standard models. So Paul was able to take his models over to the country, and they were used in the classes. Another advantage is you do have models. I mean, I'm sure you had models that you studied in your anatomy classes, but those are usually of standard patients and not therefore showing a particular medical condition. So what you can do is create a model that's based around a medical condition and actually show the model then to the students. Another thing that we were starting to work on before I left Deakin was to use this technique to create models which you could even perform surgery on. And so the idea was that because you have the soft modeling material, what you could do is actually cut into it with a scalpel. We were even toying with the idea of pumping red fluid through some of the arteries so that when you cut them, you might get blood spurts and other things going on. So sort of show some of the problems or techniques during surgery. So how to sew people up and things like that. So we were working on that. We, as far as I know, we're still doing that. Still got people doing that. Another thing where we used was, in this case, using 3D printing to create devices to help. This again is an educational model. This is a 3D printed pregnant lady. Okay? And if you see on here, there's a slight difference in material here. This is the softer material. Inside of this, there's a little robot. So it's a bit like Alien. Okay? What the robot does is it actually provides the contractions. And the idea is for a midwifery student to put her hand on the abdomen and feel the contractions. This is an earlier version which was looking a little bit more realistic, but in fact we didn't need it. We just needed something that was kind of representative of the shape, because we're using a VR headset. So what we're doing is we're relaying a VR interface. So this is what this lady is actually seeing in the VR headset, and she can look around, and there's a picture. So we've got somewhere there's a husband who's asking. He's very irate, and he's asking what's happening to his wife. Is everything okay? And then we have a TV going on in the background making noise and distractions. And then we can switch on a thunderstorm in the background as well. And the whole idea is to see whether the midwife can still concentrate on the task with all of the distractions going on. So it's a training module. And we're working on that and providing more and more realism. We're providing data from the measuring devices, the pulse measurements and things like that, in order to detect help with training of the midwife. Virtual reality. Yeah. So this is, so you see she's wearing a headset. So this is the VR screen. She also has earphones. And as she moves her head around, the view changes. So this is the 3D printed part, which is what she can feel. Because that's the thing that you can't get very well with VR, is the feeling of it, particularly of the shape. So by combining this with the VR, you get both a touch and sight sense feeling. Yeah, and sound. So 3 senses. Okay? Oh, yes, right, yes, I was wondering what this was. So I mentioned about Dietmar Houtmacher, who at the time was in the NUS. He then moved over to Queensland University of Technology, QUT. Quite a few of you know Professor Prasad Yalagada, who's a professor at QUT. So he works with Dietmar. And there was somebody who went to the he's gone now, isn't he? To the conference in Brisbane that was organized by him, and I was there as well. One of the things I was talking about was this additivebiomanufacturing.org, or rather network. Okay, do you have research hubs in India where you might have a number of universities, they group together, and then you have a number of PhDs which are paid by a fund which allows the students to move around the universities and then also to companies. So this is, in Australia they call this a training hub. And it allowed for funding of 12 PhDs and 3 postdocs to work with here. So the universities were Queensland University of Technology, Wollongong, which is near Sydney, RMIT, Deakin and Melbourne, which are all in the Melbourne region. And then these are companies that we worked with. These ones obviously do ear implants. Some hospitals, some a company that does drill plugs for skull bores. Anatomics is a company that does 3D printing for medical applications. So this is the bioadditive or additive biomanufacturing training hub in Australia, which I helped to set up. So it's a very good thing. In Europe, they have a thing called Marie Curie Foundation, and it's there for the same sort of purpose. So I'm currently looking at trying to set up a similar hub in Europe. And just to prove that also have some involvement with around here. Here we have, when I was here at the last GIAN, just before I left to get on the plane to fly back to Melbourne, Santosh said, "Come along and we'll go to see a surgery." So that's me. Is that you, Santosh? Yeah. Who else? There was somebody else with us. I can't remember. Who? It was you? Was there somebody else? I thought... Yeah, okay, all right. I thought there was somebody else from the conference apart from us. But anyway, so this is us looking at this, and this is... are you going to be talking about this at some point? Yeah. Maybe? Yeah, okay. From what I understand, yeah, you've done quite a lot of cases like this now, which is great. This is sort of, I think this is for cleft palate. Yeah? It was, okay. So, yeah, so there was quite a segment of the upper jaw was removed, I think, and then this is replaced in there, and that provides a post for the dental replacements. Very nice, very interesting surgery. I remember that this guy needed about 3 doses of anesthesia before he would actually eventually go under. So it took quite a bit longer than we initially expected, but it was a successful surgery, yeah? So just to say that we do collaborate. Okay, so again, relating back to what you might like to see. So you want to know maybe about different types of 3D printing. You want to know what is the state of the art. You want to know what's happening in other parts of the world. You want to see what research opportunities, what opportunities there are for practitioners, or what opportunities there are for business. So that's really what we want to be talking about. Kind of come to reasonable time. We started a little early, so we finish a little early. Okay, there we go. Okay, thank you. Questions again?
So, after the certification, when it was Australia regarding the medical implant, what is the basic process and which is the panel which goes with?
It's a very difficult and lengthy process. I mentioned this a couple of times already, but it might be worthwhile saying it in this particular perspective. 3D printing in a medical context like we've seen just now, surgical, can only really happen if you have a very senior surgeon and you have full approval from the patient and all of the people associated with the patient. So it's only possible to take place if in very individual circumstances. One of those circumstances might be that the surgeon actually refuses to carry out another procedure because he thinks that it might cause harm to the patient. I have a couple of examples which I might show later of stuff that we did in Singapore which might illustrate that. Certification, therefore, is a sort of an individual sort of process, if you like, on a case-by-case basis. So there's no standard procedure which basically enables you to do this on a widespread basis.
If a specific metal is used, mostly the titanium is used for the implant. However, the certification of material in terms of that one, is it done by any of the...
So FDA have approved a certain number of materials which are suitable for implantation, of which titanium is one, stainless steel, cobalt, chrome. It's the only ones I can think of, but I'm sure there are probably some magnesium-based alloys as well.
So, it's before printing, but after printing the part, you have to go through any certification of mechanical testing?
And that's a very good question, and that's where the part of the problem lay. Because if you are implanting something which is unique, how do you know that it will withstand the forces or other effects that might happen in the body, and you cannot relay that back necessarily to previous cases. So it's a problematic issue, yes. So this one is a difficult one to deal with, and this is what partly is causing a lot of hesitation in certifying it in a more mainstream basis.
So have you overcome in these special cases?
The special cases is really by, you can do a lot of numerical analysis. You can relay back to previous cases as comparative cases. You can look at the material properties and be able to get an expert opinion on those. but you cannot explicitly certify that implant. So it's based on trust. So there is actually, I think, a disclaimer process which would be included in this, which basically says if this implant fails, then you realize that there is potentially a risk that it may fail rather.
So
There's no liability.
so if that implant fails, who is going to bear the responsibility in terms of medical process?
Good question.
Because real-time challenges which I am facing in my
Yeah, but it happens in normal cases as well, where non-prototyped cases. For example, you do a hip implant. There's a certain percentage of hip implants which fail because of infection. No, infection at the interface on the inside of the bone, where the stem meets the bone. In that case, the consequences are extremely severe because you have to remove the implant. If you remove the implant, you can't really put another implant in its place. So you've got a really big problem there.
So who is going to bear the responsibility?
It's part of the process, I guess.
I mean, in terms of ethics,
I mean,
in the
Yeah,
hospitality,
yeah,
end of the day, who the panel member?
yeah. You can. Yes.
Oh, patient case. Okay. On patient case.
Yeah. Yeah.
So it's totally, that's why you are taking the inverted.
Yeah. Exactly. Exactly. And I'm glad you said that, not me. Because, you know, coming from you, it means much more, because that's exactly the kind of the point that I was trying to make. And with 3D printing, it only makes the experiment more difficult to predict the outcome. So the fortunate thing is that many cases, a large majority of the cases, probably more statistically than in the general cases, it's successful. And the reason behind that is because, as I mentioned before, the usual method or the practice, you have to have a very senior, experienced surgeon to give the green light on this. You can't just do this for anybody. There has to be somebody very highly qualified, and essentially somebody that the hospital authority and the general authorities trust in a significant manner to be able to take that decision. And that trust is built up through experience, the quality of service that's happened over the years. So this becomes an issue because, you know, if you want to have this in a more, because the best situation is actually where you can use these methods at a low level, because it's a standard routine process where medical students, surgical medical students, are trained on and able to then use more effectively. So that's the ideal, but that's not where we are.
Do they actually have any board, medical board, which are
Yeah.
what
Yeah.
is the board?
I don't know the process, but yes, they definitely have a lot of medical boards, both within the hospitals and over.
To the medical part.
Yeah. Now, this is one thing I may come across. I might see if I can find an example. There's a recent example. It was about a year ago, where Australian company Anatomics worked with a research lab to create a sternum. Basically, the center part of the rib cage. They 3D printed it in titanium. And the reason why they were involved is explicitly because it was not an Australian patient. It was a Spanish patient. So the surgery was actually carried out in Barcelona. And the reason they did this is because it's actually easier to get the approvals, if you buy an implant that's designed somewhere else and then imported. So the people, if it was built in Spain, they would have had a lot of problems. Or if the patient was in Australia, they would have had similar problems. But because the patient was in a different part of the world from where the part was made, it was actually easier. So don't ask me why, but I know that this was the case.
Yeah, it happens in India as well. Actually, we move fabricate here and then the part over here for certification and get that and exactly do it. So how about an international setting a board of doing the medical standards, like ACM for mechanical?
So last year I was involved in putting together a group, and Dr. Chicharya was involved, and also the surgeon that was in the case that I showed. I can't remember his name. He actually went to Finland. It was last year, I think. Yeah, about a year and a bit ago. Last year in April. I was hoping to go, but I couldn't. But that was part of a working group, and included some people that I knew from Hong Kong, some input from Australia, some input from Europe, to try and discuss this. And there's been a number of others. There was a similar meeting in Ireland for the same purpose, for doing exactly what you're saying, to try and understand how each country deals with this. Because in every country you have a different hospital authority system, a different hospital system, different medical treatment methods, and also different problems. Different medical problems. Whether they are to deal with first world or third world problems. In America, it's a lot of problems due to fat people. Okay, in India, it's not so much. It's other problems. Okay, and in Europe, and also in sub-Saharan Africa, for example, a lot of medical conditions related to tropical climates and things like that. So, a lot of different medical problems around the world which relate to different types of solutions and different ways to solve those issues. I once went to Vietnam, and I found out that Vietnam was world famous for treatment of head trauma. Why? Motorcycles, no helmet. Okay, I see that you have that in Warragul as well, but anyway, they drive them faster in Vietnam. So a lot of people are suffering from that, and so therefore a lot of people actually, if they want to study how to deal with head trauma, they go to Vietnam to study and to learn from the best. Same thing used to happen in Ireland during the conflicts in Ireland, because it used to be that you used to, if you were in a gang and you fell out with a gang, they used to shoot you in the kneecap. So Northern Ireland became famous for kneecap reconstruction. So, it's just the way it is, that you have different problems in different places. And so understanding all of those issues will help in coming up with a global approach to this. So this is happening now. We're not there yet. Okay? We done? We're done. Okay. Well done. You survived one day.